Come on, okay. All right. Okay, just talking a bit about the background of the course after a bit of a break over the semester break. I focus on financial macroeconomics rather than the stuff you normally find in a course on behavioural behavioural finance, which is what investors do in market behaviour. And that's really because, as I've mentioned a bit in the early part of the course, I don't really think the role of agents in the theory should be the basis of economic modelling. I think we've got obsessed with that back in the days of Adam Smith in particular, and then going on to the neoclassicals, all about behavioural utility maximising individuals and firms and trying to aggregate for that. That's been a failure, as you saw through the Sonnenschein-Mandel-Debord conditions in the demand side of the system, the failings in supply theory as well, the failings in finance. So we're better to go back to the basics and look at the dynamics of the financial system overall, taking the tops-down approach that applies in most genuine sciences, which economics is not. And later, once we've got that mastered, then we can talk about how agents behave, which is the way that modern physics and modern biology are moving these days, but after they got all the foundations right to begin with. So when you look at how sciences normally behave, they treat the system as dynamic to begin with. I'm just reading, by the way, a book that Tom Sargent, the most recently forged Nobel Prize winner in economics. I say forged rather than made because it's a farce of a Nobel Prize. And in defending neoclassical economics against the charge that it didn't see the crisis coming, he first of all argues that their models are designed for good times, not for bad times. Well, that'd be true if they didn't have models. They had models for bad times, which they don't have. But he then made a particular defence, saying there's a book that gave a good explanation of the crisis from a neoclassical point of view. Well, I decided to download it and take a look at that one. It's one I hadn't read. And it treats time by dividing dividing time into now, which is 0, and the future, which is time 1. Everything's in equilibrium, transition between the two. There is no money in the system. It's all about savers transferring to borrowers. Total nonsense, total crap. It is not a dynamic system. They think that's dynamic. They don't know what true dynamics is. So a true science uses the mathematics developed back in the 19th century, hardly recently stuff, to build a model of the relationships and causal relationships between the components of a system. Now, obviously it's not done by economists instead, and the worst is they treat it as if it's static. Their attempts to do dynamics are painfully childish. Compared to what genuine scientists do, they're so far out of touch, it's just unbelievable. And that particular book recommended by Sargent is a classic instance. They ignore the feedbacks, they ignore what happens out of equilibrium. And all the issues of change in time is completely missed out. So to actually do things properly, you've got to be taught how to do dynamics where you start from the causal relationships between the entities in the system. And that's something mean you have to learn some mathematics to do that, because you simply haven't been taught it. Okay? This is the reason most economists don't dive in and do this, is because their own training, and this applies to people that Nobel Prize winner Sargent recommends as showing how neoclassicals could understand the financial crisis. They obviously haven't learnt this mathematics themselves, otherwise surely they'd reach for it, because it's far more elegant and suitable for modelling dynamic systems than the nonsense they go on with. So in this lecture I'm going to go through the basics of how you do dynamic modelling, and then try to simulate a dynamic system overall, and start developing a model of the monetary circuit based on the logic I went through in the last few lectures. And it shows that, unlike some of the arguments that the circuitous crowd came up with, a pure credit economy works in the sense that capitalists can borrow money, invest it and make a profit, which is what Keynes argued could happen in that argument about the revolving fund of finance. So all the stuff that I went through with Graziani in the last couple of weeks about losses in the circuit, workers needing to spend all their wages, otherwise debt couldn't be repaid back, it all comes from misunderstanding dynamics. And what I'll be showing you is, in my opinion, unfortunately, the world's first explicitly monetary circular flow model, because we should have done this a century ago. It's a sign of just how much neoclassical economics has slowed down developing genuine economics. It has this, waited until I did the damn thing in 2010. So back to the circuit model, the basic proposition there that all exchanges are three-sided. You have a seller, a buyer, and a bank that records the transfer of money from the buyer to the seller, that the seller then accepts as a complete extermination of the relationship between the buyer and the seller. And it's driven from loans from the bank first of all, so I'm ignoring lending to the household sector here. Of course that can be incorporated, but to start at the purest level, I'm just looking at the banking sector lending to the firm sector. So the lender can't exploit seniorage either. This is an important point in Graziani's logic. Practically speaking, this is what a lot of banks have ended up doing, or financial institutions, exploiting the capacity to create money. So I'm leaving out that curly, that fraud does happen in the real world, but even if fraud didn't happen, you could still make a profit, everything could still work. So the bank can create credit money, but it can't spend its own notes. If it's going to have income, it has to earn that out of what it does in the circulation process. And it's necessarily dynamic, so you've got to use dynamic tools, and the conventional tools, all the diagram stuff and partial and general equilibrium, are not dynamic, nor is the nonsense of dividing time into now and the infinite future, 0 and 1 treatment of time, which neoclassicals think is fancy stuff. So you necessarily have to include time, and the simplest way of starting that is to talk about a percentage rate of change of some variable over time. So if you say population grows at 1% per annum, for example, then that's saying the percentage rate of change of the variable y, which is population here, is the slope of the function with respect to time. So that's the change in population over a time, for instance of time, divided by the current value of the variable. And mathematically, that's how it's shown. 1 over y dt equals 0.01. That's exactly the same as saying the percentage rate of change of population is 1%. Now you rearrange it into this expression, and that looks like differentiation, which you've done before, of course. You did plenty of differentiation in economics, but it's a differential equation. And the essential difference is, notice that I've got dy dt equal 0.01 times y, not 0.01 times t. Okay? That's the essential difference between differentiation and a differential equation. Now, doesn't look like a lot, but the fact that the rate of change of the variable depends upon its own value rather than on the independent function makes it much more difficult than standard differentiation. When I said you've done that many, many times, working out maximum and minimum of some function, like for example the argument that profit is maximised where the rate of change of revenue equals the rate of change of cost, and I've already shown that's wrong, okay? But because they're doing the wrong type of differentiation even there. But the idea is you take functions which are revenue and cost that are both related to quantity, differentiate with respect to quantity, put them to equal, boom. It's quite easy to do. Okay, it's wrong the way they actually do it, but even when you do it properly, it's quite easy. But differential equations are different because you have to integrate them to solve them. So you start from that expression, and what you then do is you rearrange that till you've got y and t on either sides of the equal sign. So it's treating the dy and dt like little separate numbers. Now there's a good theorem in mathematics that proves that's legitimate here, okay? I'm not going to go into the detail, but there's another more formal way to do it, but this is a legitimate shortcut. So what you then say is, well, if the rate of change of y with respect to y is equal to a times the rate of change of t, then you can integrate both sides. But what you're doing is you're integrating the left-hand side with respect to y and the right-hand side with respect to t. Okay. Now again, there's a theorem that justifies that, which again, if you do a mathematics course, you'll learn. But that means that that's only possible if both those things are equal to a constant, which again, that's part of the elaboration of the formal theorem behind why this works. Well, if you integrate dy of y, you get the log of y. And if you integrate a to dt, you get a times t plus a constant. Okay, so this is it's not hard at this stage. Then, of course, to get rid of the logarithm, you take the exponential, and that then gives you y of t is equal to the right-hand side now as an exponent, e raised to the power of a times t plus a constant, and something you can then separate out the exponential, so two exponentials added together become the exponent multiplied by the other is a separate entity. So you get e to the at plus c is equal to the e to the a times t multiplied by e to the power of c at 0, and e raised to a constant is itself a constant. So you can then say the overall result is that the population level at time t will be some constant multiplied by the exponential raised to the power of a times t. Now that constant is the value of that variable at the time t equals 0. Now I'm taking the population, say if I take the population of Australia in the year 2010, then that value would be 23 million. And the A would be the rate of change of the population, which would be about 1.5%. Okay, so that's the overall equation. Now, that model gives you exponential growth if A is greater than 0. If A was actually less than 0, so we're talking like the Japanese population situation where that's like minus 0.1, you'd have declining population over time. But unlike differentiation, that was quite easy to do. It's slightly more complicated than doing straight differentiation, but easy enough to do. Now, the problem about differential equations is that differentiation is a bit like scrambling an egg. Easy to do. Integration is a bit like taking a scrambled egg and returning it back to the state of the original egg. Very, very, very hard to do. Most functions it can't be done. There's a range of good theorems in mathematics, again, that prove that almost every function can be differentiated and almost no function can be integrated. Now, of course, most students spend their time doing lots of exercises where they do integrate to solve differential equations, but the problems are given are specially chosen to fit the conditions that enable that to happen. So most of the time you can't integrate them. There is no simple solution. And also, to make it even worse than that, you can have models where population depends upon the amount of iron ore in the country, if you like. There's feedbacks between one variable and another. So, as well as depending upon its own value, a variable can depend upon the value of other variables for its rate of change. So you get all sorts of complex feedbacks occurring in a genuine, complex, dynamic model. And they're all functions of time. I'm leaving out one other element, of course, they're functions of space as well. There's an area called partial differential equations that handle that as best as it can be done, but the range of those can be solved is even more limited than for what they're called ordinary differential equations, which just look at time. So the models end up being extremely complicated. I'll give you a simple example here of looking at the relationship between the population of fish and the population of sharks. Now, if there's no sharks, you can start with the assumption of saying there's plenty of food for the fish, so population of fish will grow smoothly. And that then, therefore, you can use exactly the sort of expression I've shown you beforehand to say the rate of growth of fish population is 8% per annum. So start 1 over FT equals A. You go through the same process I showed you a moment ago. Put F on one side, T on the other. Integrate with respect to F on one side, T on the other. Solve them, take exponentials, and you've got that expression again for the number of fish growing exponentially. And I can then simulate that and get this sort of outcome. There's an equation which actually puts the whole lot together. So I've got a population growth of 2% per annum, which is extremely slow for fish, of course. Starting with 100 fish, I'm saying fish at time t are going to be fish at time 0 multiplied by e raised to the power of a times t. And that's what it shows me. If you go for 100 years, you'll have 7 times as many fish as you started with. Now, I can do exactly the same thing for sharks. But now what I'm going to say is their population falls. Unless there are fish around there, they're going to starve to death. They'll eat each other to begin with, but then they'll ultimately starve to death. So it's negative. So I do exactly the same expression, and then I plot that and say we start from 50 sharks, and over that period of time, again, quite unrealistic numbers, just giving you an illustration, they'll decline to 0 over time. But of course they interact. So the rate of change of fish is also some negative function of how many sharks there are. So I can now add that in at the simplest possible level to say, well, let's just use the simplest possible function to take that into account and say the relationship is some constant times how many sharks there are. So now I'm saying 1 over FDT equals A minus B times how many sharks there are. And equally for sharks, same sort of expression, I can say it's some positive function of how many fish there are. So I get 1 over SDT equals C plus D times some value for the number of fish there are. Now, it's now a model where the rate of change of each variable, fish and sharks, depends upon its own value, but also the value of the other variable, sharks and fish. That's the very beginning of a more complicated model. Now, that is actually possible to be solved. If I play around with this a bit, I get those two expressions there. I've multiplied across by the 1 over S and the 1 over S to make them semi-quadratic equations over the other side. So there's F's being an argument in the fish, and there's F being an argument in the sharks as well. So you can still solve that, but it takes a lot more effort. And I'm going to show you how to do that, just to show that it can be done. But this is the last piece of solving I'm going to show you. Now we use a trick here to say 1 over f df dt is equal to the differential of the log of f. That's again another straight principle of mathematics. So I can then say that the differential of the log of f is equal to that expression, which is entirely in terms of sharks. And now I can apply the same basic expression of saying I can integrate the left-hand side with respect to fish and the right-hand side with respect to sharks. So I do that, and the integral of the differential cancels out the integral, well, they're opposite operations. So I'm left with the log of the number of fish is equal to a minus b times s times t plus a constant. Go through and solve that, and I've now got an exponential that, as you can see, as well as being e raised to the power of a, which is a constant, is minus b times how many sharks there are. And the same basic story applies with sharks. I get this negative times minus c, a negative value there, plus d times how many fish there are. Now that is absolutely the last level of complexity that you can get an analytic solution for. This is again one thing I find bizarre about economists. They don't realise the limitations to mathematics that are commonplace in knowledge amongst mathematicians. If you add an additional variable that it says, I said, well, the fish can't actually grow exponentially. They've got to eat seagrass, and if they eat seagrass, they reduce the level of seagrass. That'd be a three-system and more realistic model. That cannot be solved analytically. There is no analytic solution. But you can, of course, because this sort of stuff is important, you can find other ways of simulating the system to see what actually does happen and get an accurate simulation, even though you can't get an analytic solution to it. So mathematicians have shown that you can actually do this, and engineers have built tools to make that quite straightforward. And if you're doing an engineering degree, as some of the members of the audience have done, you'd be learning this sort of stuff virtually from day one. Where did you actually start learning systems dynamic software? Sorry? Third year. You did get there, okay. Now what you do, I'm going to use the mathematical approach here to show how it's done at the level of equations. So I'll put in a couple of values for A, B, C and D. The first, A is the annual rate of growth of fish in the absence of sharks. B is the impact of each shark on fish numbers, or the fish growth rate. C is the death rate of sharks in the absence of fish. And D is the impact of each fish on the survival level of sharks. Now calculate the equilibrium, and here's a cute outcome, by the way. The equilibrium value for the fish depends upon the parameters for sharks. And the equilibrium value for sharks depends upon the parameters for fish. So you get a classic instance of interaction between those two variables. Then, rather than stopping at that point, I can simulate it. And this is using my favourite mathematics program, MathCAD. One reason there are many other programs that will do this, Mathematica, Maple, MATLAB, that engineers tend to use. What I like about MathCAD, it actually expresses the equations literally as you'd write them on paper. So that's, you can read the equation there. It says, here's your differential for fish, there's your differential for sharks, differential equation, here are your initial values, and just these key words around the outside given and then ODE solve. So simulate that for a number of years, 10 years, and give me 1,000 time steps at that. So I'll have 100 values for each of the years doing. So do that, and what you find, and this is the important insight for people who have been browbeat by neoclassical economists, the equilibrium is unstable. It's actually neutral. It repels as much as it attracts. And that's a commonplace thing in dynamic systems. Nothing, in most dynamic systems, nothing ever happens in equilibrium. You're always outside the equilibrium. So you've got to model systems that are far from equilibrium, and certainly the economy is obviously one of those. So this is a very, very simple model here. And that's the outcome. The number of sharks and fish cycle out of phase all the time. You run this model for 1 million years, you'd still have those cycles going on. And there's the equilibrium in the middle of the whole thing, and there's the actual time path of the fish and shark numbers, graphing the fish on the vertical axis and the sharks on the horizontal. So that's such a simple system, and yet it generates a neutral equilibrium where the time path is away from the equilibrium. What odds that the economy is anything other than the same, far more complex system? So that's actually, what I've shown you there is, because you've got to work in equations, what you might call the hard way of going about it. But it's also possible to simulate these things using flowcharts. And this is where engineers come in the courses that engineers do normally in third year, which we just heard a moment ago. and that is to numerically integrate the rate of change of a function to work out its current value, which is being done by that simulation and math cut I showed you a moment ago, but tie them together using a flowchart. So I'll take the population growth model again, and that's saying population grows at, say, 2% per annum. Well, as a mathematics, this is what you get. 1 over p dt equals 0.02. The numerical solution then puts the p on the other side. Rather than modelling across by dt, you multiply across by p. Symbolically, you'd keep on going through the whole process, but you don't with the numerical. You stop at that point and you do an integration. So you say, if dp dt equals 0.02 times p, then p is equal to the integral of 0.02 times p dt. Now, as a flowchart, that's what it looks like. And just to take you through how these bits correspond, read it backwards. You get exactly the same equation. So there's p for population. There's population in the flowchart. There's the integral sign. That 1 over s is the integral operation. It's because the person who first gave us the mathematics to let us do this, Laplace, found a way of converting differential equations across to algebraic expressions like quadratics and so on. And he used 1 over s as the operator to go from integration to algebraic expressions. There's 0.022, there it is here in the flowchart. There's multiplied by. That's symbolic structure there, says multiply the two inputs and give us the result as an output. And there's p again. So it's basically the same story, just read them backwards. Now you feed in an initial value, let's say there's 18 million, which is the population in Australia when I first put this particular set of slides together, and simulate over 100 years, that's what you get. We'd have 130 million Australians by, I think it was by 2100. Now that's a very simple model, obviously, but this software is used to build much more complicated models, and the package I'm showing you here is called Simulink, which, is VisSim, which retails for about, I think, 1700 if it's bought commercially. And the rival package, which dominates the market, is part of this package called MATLAB that engineers use. I think the retail price for that is $20,000 a copy, isn't it? Okay. You don't pay 20 grand for toy software. Okay. Now Simulink, I regard VisSim as actually, I prefer it. It doesn't have the same mathematical engine running behind it. But to give you an idea of how complicated these can be, this is a VisSim model of an Indianapolis 500 racing car. And you notice those blue boxes there. They're containing other elements in the system. They use the boxes to structure the whole thing. So there's a box there called System Dynamics, describing the forces operating on a car as it goes around an Indianapolis 500 racing track. Let's zoom inside that, and you find it's got those various blocks there, the mass of the car, the dynamics of a rotating mass, etc., etc. Let's just take a look at one of those blocks, acceleration and braking logic, and see what's inside that. Well, it's got 4 inputs: lateral force, normal force, radius of curvature of the track, and mu. I don't know what mu would actually represent. It's the Greek term, obviously. This particular program doesn't let you put symbols in Greek terms, but it all feeds into another block, that one in the middle there. Well, let's just take a look inside that and see what we find. That's what it contains. Okay? They're not toy software by any means. And it's literally designed, used these days, most new products, like for example the Boeing 777, the Dreamliner and so on, they're simulated in this sort of software before they're built. Okay? So this is seriously used to design the modern world. And it just shows again how far behind economists are, that they don't even use this stuff, and most of them aren't even aware the software exists. Now, I'm going to use that to build that fish and sharks model. So I'll start with population, and then change it, population to fish, and then alter the design to allow for different initial numbers of fish inside there. So what I've got there, I was saying here's 1 over it, this is the same population equation. The number of fish is the integral of the number of fish multiplied by the growth rate added to the initial population of fish. Okay, quite simple model there. Now that's equivalent to the first half of that expression. I haven't got the shark bit inside there so far. So add in the second bit, I've got to alter part of the model to the left-hand side of the integrator there. So rather than just having this direct feed from the multiply sign, I've got a plus sign turning up here, adding in the impact of the shark numbers. So, and I'll just show them as a constant first of all. So what I've now done is I've added in this plus and minus block here. I've said the value is now equal to the original expression minus the number of sharks multiplied by a constant, which is the interaction of a constant multiplied by the number of fish. And that's taking the same nonlinearity I showed you in the mathematical model. Now, what they do is they simply subtract from the growth rate of fish, but there's no interaction going on there. So what I need to do is add in shark dynamics as well. So I've now got the number of sharks over here being a negative function. That's the sharks die in the absence of fish interaction. Now what I'm going to do now is add in the interaction between the two species. I'm racing through this because I'll show you another modelling package later that covers the sort of stuff we need to do. And what I've now done, the overall flowchart here, now has the interaction between the number of fish and sharks subtracting from the growth rate of fish, ditto from sharks, and what you get is this spikes in the population of the fish, spikes in the population of sharks. You plot the two against each other, you get shark and fish numbers cycling indefinitely. And I'll just show you that quickly. Okay, now what I've done here is I've put those blocks into compound blocks. If I right click here, I dive inside and you can see the structure there, equally on the sharks. And if I simulate it, you get that forever cyclical behaviour between the two variables. And again, this is the beauty of dynamic simulation software. You can actually see the stuff happening in front of you. Your whack and controls there and so on. This is how simulations are made for the control panel in a 777, simulated before it's actually flown. Now, let's apply some of this to endogenous money. But the first thing I'm going to show you is that flowchart stuff is great for the sort of stuff engineers do, where there's a flow of petrol through an engine or the flow of air through it, and you need to break down like the component for the fuel feed, for the component from the mixing of the air, from the component for the engine block and so on, and tell engineers what the inputs are going to be, what outputs they need to be, put a team together to do each of those, and they then bring it all together. That, first of all, is difficult for economists to understand. A colleague of mine, Trond Andresen, who's a systems engineer in Norway, who's involved in economics as well, tries to give presentations based on Simulink to economists, and he talks about them getting what he calls the me-go effect. My eyes glaze over. Audience just loses touch with it. I found this too a problem. First of all, that there's that grasping the logic problem, having not been trained in the area. But the main problem I find is that the flows are so hard to work out when you try to put financial flows into that flowchart paradigm. Because when you take account of a loan, where you're lending money from a vault to a borrower, you've got the same term turns up as minus in one place and plus in the other. And then you've got to record that it's actually happened in a third place. And what you start getting in terms of these modelling programs is spaghetti. Wires going everywhere, connecting the different inputs together. It gets immensely complicated. So I instead realised some time ago, courtesy being challenged by Scott Furwiller, as it happens at a post-Keynesian conference, that you could actually use double entry bookkeeping to build this model and show it in a much more realistic framework. So the idea is that each column in a model is going to be a particular account, and the rows record operations between accounts or things like recording the new compound of the debt. And you then symbolically add up the columns, not numerically but symbolically, so it's not like a spreadsheet. It's like a spreadsheet, but it's not doing a numerical addition here, and you get your dynamic model. So it's still a very new approach, but I think it's actually much easier to follow than flowcharts for financial flows. It doesn't work for physical flows, which we need to still model in that flowchart approach, but it does work better for financial flows. So here we have the stock in a column, the flows between them, and you then specify the relationships across the table. So that's the basic idea. The stocks, which I've said are almost always going to be financial accounts, the flow being, this is the minus goes from here to here, and the relationships between the accounts go horizontally. Now those two sum to zero, but that's not necessarily the case, as I'll show you later. And you generate the model by simply adding up the symbolic entries in it. And I'm using continuous time here too, by the way, which again economists don't seem to understand, rather than what they call discrete time. So there's the differential equation for A, for B, etc., etc. And you then built your quite complicated model for the financial sector without needing to do the difficult wiring that applies when you try to do this using packages like Simulink and VisSim. So looking at the initial model that Graziani gave us in that 1989 paper, he talks about the first step being granting credit to firms so that they can start production. Now, what I'll illustrate here is the bank doesn't actually need reserves to lend from that. Okay? I'm modelling a 19th century banking system. The status that the bank has allows it to create money from nothing. That's what you've really learned from the endogenous money approach. It's a double entry bookkeeping operation that creates the money. So you make an entry of L dollars in the deposit account, you make a simultaneous entry of L dollars in the debt account, which is recording how much is owed to you, and that creates the loan and the money simultaneously. So here we have the same basic idea again, is enabling to start production by that grant. So it starts with the bank sector making a loan of L dollars to the firm sector, and you need three accounts to model this. You've got to have money being added to a deposit account, the record of the debt kept by the firms in a loan account, and L gets entered into both of them. And then you've got to give interest. You've got to pay interest on this to the bank. So you need an equity account for the bank. I'm calling it BD for bank deposit account here. And we'll use a table to record the flows initiated by the loan. So the first thing that happens is once the loan's actually there, the bank is going to charge compound interest on it. It's going to, as long as the loan's outstanding, it'll put interest on the amount outstanding. And then the firm has to pay interest on the deposits balance. And you all begin and end in the bank accounts here. I'm looking at everything as if, it's like modelling the 19th century when bank notes were used for making loans and so on, physical bank notes, but I'm actually pretending that the notes remain in the accounts all the time just to simplify the analysis. Again, I could include money going into cash, but there we get the basic starting system. So I'm saying there's the firm's loan, which is an asset of the bank, the firm's deposit, which is the liability of the bank, and the equity of the bank is the amount of money in the bank deposit. A few accounting students here, I take it. This is putting the basic equation of accounting into operation. I've got to thank accounting staff if they're telling me that because I didn't do accounting. So you have compound interest. That's just going to be an entry A right now. It's just a placeholder saying it happens. Then deposit interest, because there's money in the firm's deposit account, there's a transfer of interest on the deposit by the bank. Then the firm pays interest. It transfers money from its deposit account across to the safe, and the bank then records that's happened. So you say, what's the overall dynamic? What's going to happen to the accounts? Well, the overall rate of change of FL with respect to time is going to be A minus C. DDT of FD will be B minus C, and DDT of BD will be C minus B. So this is what I'm looking at here. The basic right now are the banks to charge compound interest and then to pay interest on deposits. And the bank recording all those payments as a reduction in the outstanding debt. So there's the various transfers going on there. So let's try to get some numerical handles on this now. So the firm will pay interest to the bank at a loan rate, which will be RL, and the bank pays interest to the firm at a deposit rate, RD, and of course RL will be higher than RD. So A is going to be the interest rate on debt, which is RL, multiplied by the outstanding debt at any particular point in time, which is FL, and B is going to be the interest rate on deposits, RD, times whatever's in the deposit account, FD. And so if the firms actually pay what they're required to pay, of course, in the aggregate, some firms don't pay their debts, so I'd need to have this being shown up as C being less than A, but for simplicity here, I'll assume they pay all their interest bills, so C is the same as A. And that therefore means, of course, the loan remains the same. You compound the debt, you pay the debt, the bank records that the servicing of the debt's been done, so the FL remains constant. So this is your overall equations now. So there's the compounding of the debt. Here we go. Compounding of the debt there, payment of the debt over here, C therefore being the same as A, the sum is 0 for that particular account. What's going to happen to the deposit account? There's a positive entry here, which is less than this negative entry over here. And exactly the opposite applies the bank deposit account. What you're going to see over time is that all the money is going to transfer across to the safe. So the rate of change of the firm sector's debt is 0. The rate of change of the firm sector's deposit account is the interest payments on deposits minus those on the loan, RDR, FD minus RLFL, and the exact opposite applies to the bank sector's equity account. Now, of course, that's only the very beginning. You don't just borrow money and leave it sitting in the bank paying interest on it, but you can model it. So I'll show you the system that I use to do that, which is written in MathCAD. And you could use any other modern language like Mathematica, Maple, MATLAB. There's a free one, Psychos, I think it's called. This can all be done in those various systems. But I prefer, again, the way that I can represent this in MathCAD much more effectively visually. So there's my basic relationship. That's exactly the same table I showed you in text beforehand, but I've now got A, B and C being symbolic entries in a computer program. Now I then make substitutions for A, B and C. So I'll define A as being, as I've shown you, the interest on loans. Where is the cursor? Interest on loans multiplied by the amount of money in the firm loan account at time t. B's interest on deposits times what's in the deposit account at time t, and C's the same as A. And what MathCAD returns to me is that system. So the differential, it just shows me the differential of the loan account will be 0. The rate of change of FD is going to be the expression I showed you on the previous screen. VD the opposite. Now let's enter some reasonable values here and say the interest rate on deposits is 1% and on loans is 5%. And say we start from where there's an initial loan of $100 or 100 million, whatever. So the initial deposit's exactly the same. Then what you're going to have when you simulate it, and that's the simulation block now. Again, very straightforward, very much the same as I put it on a PowerPoint slide, as I did. And what you get, firms go broke. No great story. The loan remains constant because there's no repayment of the loan as yet. The firm deposit account falls, the bank deposit account rises, and ultimately all the money transfers across to the safe. So what you get out of that, when I graph it, are those dynamics. The red line is the amount of money outstanding in the loan, which remains there. The blue line is the amount of money that the firm sector has in its deposit account. The red line is the amount of money the safe is in the bank safe. So I can simulate that, again, with a flowchart approach. Now, start taking a look here. We're getting moderately complicated. And notice I've got FD turning up here, but also turning up down here. Multiple locations where it turns up. This is actually easier in VisSim than Simulink, as it happens. Simulink has finally enabled us to put variables in different locations on a chart, but it gets very, very messy as we get more complexity than that. Now, I'll give more detail in the second half of the lecture, but it's also possible to model this in a new software package that's been written for me by one of my blog members. And it actually uses that double entry bookkeeping approach. So rather than something as hard to read as that, I mean, if you look at it, after a while you'd work out what's going on in terms of the accounts. But I think looking at this down the bottom here, it's much more obvious. So as an interface for financial dynamics, it's better to do it this way than the flowchart approach. Now, what this model does as well, what Sirius put together for me, is you can actually then generate a model that, similar in some ways to the Simulink VisSim approach, shows the flows between stocks here. So there's the amount of money in the firm's deposit account, that's in the bank deposits, that's the payment of interest on the loan, that's deposit interest in the opposite direction, and here's the accounting operation to record the payment over here. And I'll show you that in more detail in the second half of the lecture. Graphing it again, the same sort of thing you saw in the VisSim model a moment ago. So if that's all they do though, they only simply borrow money, they go broke. But of course they do more than that. What if they then hire workers, produce output, and workers and bankers consume what's produced by the firm sector? Well, I'll show you that in the next half of the lecture, and I'll build it dynamically as we go through.